Our next graph topic is going to be on minimum spanning trees. And this is a topic that I believe everyone should be familiar with already. So I'm not going to go into a huge amount of detail, but I want to kind of review the methods and talk about a couple of little extensions to the minimum spanning tree problem. So the basic idea of a minimum spanning tree is that you have a graph with undirected edges, and these edges are going to have some weight to them. So, let's just say they have weights 1, 2, 3, 5, 7, 8, 4. Okay. That's not a very great list. But the idea is, can I create a tree? And remember, a tree just means that there's only one possible route between any pair of nodes. It doesn't mean that you have to necessarily identify the root. We want to generate a tree that's of the minimum weight. That's where the minimum comes in. And so what that means is we want to find which edges to keep out of all of the edges so that the cost is minimized. And this has some very practical applications. So one of the early ways that you can think about this is if you have a bunch of nodes and there's some cost to connect them and you want to put them all in a network, what's the cheapest way to connect all of them? So maybe these numbers that are over here are the cost to build a link between those two nodes. And so you want to get the minimum cost, or it could be what's the cost to build a road and connect all of the cities, or a variety of other things. Okay, so minimum spanning trees, they have a lot of practical use. And what you'll get out of it is you will find that the minimum spanning tree is going to be, in this case, it's going to be those edges that you have there. And so we don't use the edges 3, 5, or 8 in this particular example. It's that example, the edges that you see there are the minimum way of connecting all 5 nodes in the graph to one another for the least possible total cost. Now, there's 2 actual algorithms for computing this that are commonly used. So the first one is Kruskal's, and the second one is called Prim's. And so we'll get to Prim's in a minute. But the idea of Kruskal's is that we are going to be looking at a global list of edges. So we will look at all edges, and we will pull them off in order from lowest weight to highest weight. So we'll take the lowest weight at highest. We'll take the lowest weight edge and all the way up to the highest weight edge and pull them off one by one as we do that. And when we do that, we will say if they, well, basically we don't even have to necessarily write the if. We'll just say that we will merge those nodes into the same set. And we will repeat until all the nodes are in a single set. So I'll do an example here. I'll just sort of show you how Kruskal's will work. But when we talk about merging things into sets, when we talk about that is our very familiar union find structure. That's our disjoint set operation. Okay, so let's say that we've got a graph. I'll just draw the graph down here. So we'll have nodes. Say we've got maybe 8 nodes, and we'll connect them up with different edges. Okay, something like that. And I'll give all of these edges some different weights. So maybe some of them will be nice small weights, and we'll have some medium weights and some bigger weights, and so on. So just to give an example here of what this might look like. Okay, so there's a graph. Those are the edge weights. Just to make it easier to talk about these things, I'm going to label the nodes so that I can refer to them and you'll know what I'm talking about. Okay, and so at the moment, when we first start out, we've got all of the edges, and we would keep them in a sorted list from lowest weight to highest weight. And so, for instance, what this would mean is our edge list, our sort of global edge list. And notice this is one of the cases where a global edge list is actually all we need for the graph representation. We don't need to keep an adjacency list or anything like that per node. The global one works fine. So we'll have one of weight 1, that's the one that's from B to C. We have one of weight 2, that's the B to E. Let's see, I see one down there that's 3, that's G to H. There's one that's 4, that is H to F. I see one that's 5, that is E to C, and one that is 5, that is E to H. There's none that are 6. I see one that is 7, that is D to G. I see 8, which are EF, and I see one that's 8, that is AB, and 9 are going to be DE, 9 is AD, and 10 is D and B. Okay, so there's all of the edges, I believe, unless I happen to miss one. They're in order from lowest weight to highest weight. And so we start out with everything in its own little set. So everything, each node is just in its own set. And we'll pull out these nodes these edges one by one. And if it is an edge that connects two things that are in different sets, then we'll merge those into the same set and call that and do our union find there. Okay, so the first one that we pull out is this edge 1 B to C. So I'll mark that in blue. These B and C are in separate sets. So I will connect them. I will keep that edge, and I will mark that B and C are now in the same set. So we start out with all 8 nodes in its own, each one in its own set. Now B and C have been merged. So now we go to our next one. We have BE. So we look at B and E. Those are in different sets. Those are not in the same set. So we will again keep that edge, and we will merge B and E into the same set. So notice now B, C, and E are all in the same set at this point. The next thing we do is GH. Again, those are separate sets, so we will keep that edge. That is one that we want, and merge G and H into our sets. So at this point, notice we have a set A. We have a set that has B, C, and E in it. We have a set D. We have a set F, and we have a set that has both G and H in it. Okay, so those are our sets at this point. Our next edge is HF. So again, those are different sets. H and F are in different sets, so we will merge those two together along there. And our set now, F has gotten joined in here. The next edge is EC. And notice E and C are already in the same set. Both of those already exist in the same set. And so that edge is not one we want. We don't care to use that when they're already in the same set. We don't want to add that to our minimum spanning tree. Our next edge, EH, is going to be E. Since E and H are in different sets, we will again join that. We'll keep that edge in there. And notice now that these two sets have gotten merged together. So at this point, we just have 3 sets left. We have A, we have D, and we have B, C, E, G, H, and F, all in one set. So 3 sets total remain at this point. Again, continuing on, we pull out DG. So DG, that does add a new edge. We get that one right there. D is going to be joined into our nice large set here. EF. So from, and I'm realizing I have one edge I never put a weight on. So let's just call that 11 to make it big. So EF is going to be 2 things that are already in the same set, so we don't use it. And then we pull out AB. AB is, again, a new set. And at this point, we've now connected everything up. So A has gotten merged in. So everything is all in the same set at this point. So there's no further work needed. We don't need to keep processing the edges. Notice we had a couple of them along the way, including the one that I never listed down here, which was 11 from D to E. Sorry, and this one was not D to E. This must have been G to E. Okay, but anyway, those aren't important. And so notice if you just look at the blue edges here, that's our minimum spanning tree. Every node is connected to every other node. There's no version of this that would be any smaller along the way. And again, this is Kruskal's algorithm. So this is the union find. You use your voided list and you just add in elements one by one. And notice every time that we add a new element, every time we colored one blue, we could have been keeping a total of the total cost if we had wanted to. All right, so our second algorithm is called Prim's algorithm. And both of these are greedy algorithms. They work a little bit differently, but they're basically the same idea. So the idea of Prim's algorithm is you will start from an in, I'll call it an in node. So we mark one node as being in, and then we're going to basically be gradually expanding, and we will keep a list of all edges from the in nodes. So we'll say we want to keep track of all of the different edges that we have across all of them. So what we will do then is we will keep pulling out the next smallest edge. So you can keep this in a priority queue, that list of edges. And if it is to a node that has not been added to the in group already, so if it's to an out node, then mark that node in, and add its edges to the priority queue. And you will repeat this until all nodes are in. Okay, so that's the idea. There is we'll just do this. So let me I'll demonstrate this. I'll try to do the same graph that I had before if I can remember all of the elements of it, and hopefully not leave one of the edges out this time. Okay, so first of all, we have A, B, C, D, E, F, G, and H. Okay. And this one was 3 and 9 and 5. This was a 5. I believe we had 11 here, 10 here, 9, 8. This was 7, 2, 1, 5, 8, 9. Okay, so I'm going to use blue to indicate when a node is inside, or blue for the edges, and I'll use green for the nodes. So we start out and we mark some node as in, and it doesn't really matter which node we start with. I'm just going to start with A because, hey, it came first alphabetically. Okay, and so we'll mark A as in, so that means we say this is now in, and we're going to add a priority queue of the edges that are from A. And so the edges that we have at this point, so this is going to be my priority queue over here. I'll just keep a list of edges and hopefully update it as we go along. So one of them is going to be an edge of weight 8. That is A to B, and we also have one of weight 9 that is A to D. Okay, so the next thing we do is we pull out the first thing off of the priority queue. That's this one. And so that's going to be from A to B. Notice that B is an out edge. A is in, but B is out. So we will mark V as in. And now we will add all of B's edges onto the priority queue. So this one we can remove. We just popped it off. We add all of B's edges on there. So remember, it's a priority queue, so these will be in sorted order. So we'll have 1, which is BC, and we'll have 2, which is BE. And we will have 10, which is BD. And if we wanted to, we could add in BA again, since that's one of B's edges, but we don't have to. And notice this works well if you have an adjacency list formulation where each node knows what its own edges are. Okay, so again, we pull out the first thing in the priority queue, the lowest valued edge. That's this edge BC, and I'm sorry, this was the one that we have added in already. So the next one that we have is BC. Since C is out, it's okay to use this edge. So we will mark that edge, or we'll mark that node as in. We'll mark that edge, and now we can erase it. And we have to add C's edges in there. So the edges that we have from C, we have one of weight 5, which is CE, and we have one of weight 9, which is CF. Okay. All right, we pull out the next one. This is the edge of 2 from B to E. So again, E is another out node, so it's okay to use this edge. So we pull that out. We mark E as being in. This is now no longer on the priority queue, and we have to add E's edges into the list. So E is going to have, well, it's got one of weight 11 from E to D. It will have one of weight 8, which is from E to F. And we also have one of length 5. We have 2 of length 5. We have one of length 5 from E to C. Notice we already put that one in here. It's already sitting in here, but we don't know that yet. So we're going to have to stick it in the list another time. We have one of weight 5 that is E to H. And we have one of weight 9 that is E to G. So I'll just point to it in here. There's one that is 9 E to G. That's at that point in the priority queue. All right, so now we pull out our next one. Our next edge is going to be this one, weight 5 from E to C. Notice, however, that both E and C, both nodes here are already in, and so we don't do anything with that edge. It's marking 2 things that are already in. We pull out our next edge, which is 5 from E to H. H is not inside, so we will mark it. We'll say that that's a length that we want along the way, and I'm realizing I left that one off. We'll mark that one along the way and add H's edges in here. And so the edges for H are going to be one of 4, size 4 from H to F, and one of size 3 from H to G. And we don't necessarily have to put the one that we're marking at the time, since we know what it is. Although if we did it, when we pull it out later, it's just going to give us E to H again. Okay, so continuing on, we pull out the HG. That will, since G is not in our set already, we will add it in. And that means that we have to add G's nodes in here. So we get one that is going to be 7 from G to D. And we have one that is going to be another 9, which is G to E. Okay, that goes away. This is my priority queue. So we pull out the next node for H to F. So H to F, that's yet another new one that we can add in. And we will add in another 8 from F to E. And we will add in yet another 9, which is F to C. And that goes away. All right, so we're almost done here. If we pull out edge CE, notice that C to E, both of those are already inside, so that we don't have to do anything with that. The next thing in our queue is this one, 7 G to D. Since D is not in our set already, we go ahead and we add that one in, and we build that up. Okay, and at this point we're done. So at that point now we remove that, and we are done. All of the nodes are connected up. We've added enough edges to connect up our entire tree, and you'll see that that tree and this one up here, those are the same. They're the same trees. That's the same nodes connected. Both cases, it's the minimum, but there's different routes of going it. So Prim's algorithm, this second one, it's sort of like an expanding front. Okay, so you can notice we started with A, and then we kind of added B in there, and then we expanded that out to include, actually, I think we included C next, and then we included E, and then we included H, and then H included G, and then G included F, and then finally we expanded out to D. So it's sort of this expanding wave front that spreads out from where we started out. Whereas back up here with Kruskal's algorithm, we sort of built things in different pieces. So different parts of the graph got kind of connected together at different times. Okay, so those are the main minimum spanning tree algorithms. I do want to mention just a couple of the variations on minimum spanning trees that you can have. You can actually have a maximum spanning tree if for some reason you wanted if you wanted to pick the biggest possible weighting node. And if you want to do that, what you would do is you can just run Kruskal's algorithm. It doesn't work with Prim's, but Kruskal's with the edges sorted greatest to smallest. Okay, so if you still want a spanning tree, but the greatest possible weight, you can use Kruskal's algorithm with greatest to smallest edges. Sometimes you'll see something where you have a subgraph already defined. So you're given a graph that, so if it's a spanning subgraph, okay, this might be where you've got a set of nodes and you say, well, I've already got a connection here and I've got a connection here. What's the smallest way to connect those up? And basically, you can just run Kruskal's with some things already union together. Okay, so it's just a variation on that. You know, here you might connect that one up, and you might connect that one up, and now you have a minimum spanning tree where you kept the certain links already in place. So not particularly a tricky way of doing this. I believe you can also use Prim's algorithm in this way. Also, it's just you group all of the edges. You know, I'd have to look at every possible edge coming out of these and start with all of them to find the one that I add and merge and join these sets together. And then anytime you connect to one thing, you also have to connect to everything that it's connected to. Kruskal's will be a little bit easier because you already have this idea of certain things being disjoint sets already because they're regions that are already connected, and you're just connecting up the regions between them. Okay. So that's a spanning subgraph problem. Another variation is you can have a minimum forest. So a minimum spanning forest means maybe I don't need to connect up every node. Maybe I can get away as long as I've got 3 trees at the end instead of just 1. And so the idea here is you just run Kruskal's until you have X sets remaining. So you just basically run Kruskal's algorithm until you don't need to run it anymore. It's still going to be the minimum. And so you might end up with sort of 3 groups or 10 groups or however many it's going to be, but you get a forest, you get multiple trees instead of a single tree. Okay. Another thing you can do, another kind of variation on the minimum spanning tree, is you can do something that's like a second best tree. So you say, well, maybe I don't want the I don't want the minimum spanning tree. I want the next best thing I can do besides the minimum. And so this is actually a little bit trickier than you might think. You might think, oh, well, I just remove the lowest weight edge and somehow connect it up, but it doesn't really work that way, because it might be that if, maybe I had something that was edge weight 1, and if I remove that, I say, well, now I have to use this edge that's 9. Well, the net result of all of that might not be the second best spanning tree. It might be that you want to have, and it doesn't work with 3 nodes, but you might actually need to, instead of eliminating that 1, it might be easier to eliminate the 6, because you end up just adding in something that was 7 instead of having to go from 1 to 9. Okay, hopefully that makes sense. Here, I'll illustrate again just with another example. So imagine that we have something here that has connections of 1 and 9. Okay, and let's just say that this is 5. And we've got something here that is 7 and 3. Okay, so our minimum spanning tree is going to connect to that and that and this. And so we say, what is our next best one? Well, one option would be, oh, let's remove the lowest weight edge. We could say, hey, what if we remove that edge? Well, then the only other way to connect it up would be we'd have to add this one over here in. But notice that is not going to be our second best spanning tree. Our second best spanning tree would be to remove something, would be to actually keep the 1 in there, and probably remove this 5 and remove that edge, and instead keep the edge down here. So it sort of increases the cost by 2. So basically the second best spanning tree is the one that's there in green. And so the way to do this is, it's basically a brute force check. You're going to remove every link in the minimum spanning tree one at a time and rerun. Okay, so unfortunately, it's like a brute force approach. So you have your minimum spanning tree. Well, take one of those links out, rerun your algorithm, and get the next one. And you do that for every possible link, and you pick the minimum along the way. It's kind of an ugly brute force way of doing things, but it will actually work. And it multiplies everything by order n, because you're going to have n, where n is the number of nodes. You're going to have n minus 1 edges in the minimum spanning tree. So you're going to have to run your minimum spanning tree algorithm n minus 1 times. Okay, and so finally, there's one other example, which is a minimax spanning tree. And so the idea here is that you want to minimize the maximum edge weight along any path from one node to another. Okay, so if I'm going from node I, and maybe I shouldn't say minimax spanning tree, but you want the minimum of the maximum edge from I to J. So if I have different routes that I can go through here, and maybe the thing I care about is not the like shortest distance, but the shortest, I actually want to minimize the highest edge weight. Okay, so sometimes the cost you pay, it might be that as long as you're paying low costs along the way, if you have to pay 5, that the cost of taking this top route here would be 5. It's just the maximum of those edges. And so if I'm wanting to get from I to J, but I want to minimize the maximum edge, well, you can do this by just following, the key here is you just follow the minimum spanning tree edges, because you're guaranteed that the highest edge along the path from I to J, there's not going to be any other route between I and J other than following along the minimum spanning tree. Any other route is going to have some edge that's higher weight along the way. And that's by definition of what the minimum spanning tree is. You're guaranteed that that's the case. Okay, and so if you need to, just illustrate it with a couple of examples, and you should be able to see that pretty easily. That if I'm trying to connect this node to another one, and I've got lots of different routes through this thing, okay, something like that, that if I know what my minimum spanning tree is, and let's just say that the minimum spanning tree is this set of nodes here. Okay, well, if I'm wanting to go from the beginning to the end, my route to get there is going to be from here to here, here to here, here to here, here to here, here to here. So that's going to actually be the one that has the minimum possible maximum edge weight. And you can think, even if there's a more direct route, one of those edges that I've left out there is going to be bigger than one of these that was along this path. Otherwise, it would have been used, right? We would have put it in the minimum spanning tree. Okay, so that's sort of an overview of minimum spanning trees, a couple of the other applications that you can have with them. And hopefully that's a good reminder and refresher for this topic.